So I'm going to start a separate recording because I don't want the synthesis of alkenes or the synthesis of carbonyls to be in the same video as the reactions of carbonyls. And this kind of gets at the question that you just asked, which is kind of what class of reactions do things fall into? And the reactions of carbonyl compounds are in many cases nucleophilic acyl addition reactions, where we're taking that carbon-oxygen double bond and we're adding something across it. So we're taking acetaldehyde, for example. Right? If we react this with some reagent AB, such that we get A attached to the oxygen and B attached to the carbon, and I intentionally made it AB acid base because it's the delta plus part that's going to end up attached to the oxygen, and the delta minus, the nucleophile, is going to end up attached to the carbon because of the polarity of the carbonyl bond. So that is a nucleophilic acyl addition. We added something across the carbon-oxygen double bond, and now we don't have a pi bond anymore. So you know two examples of nucleophilic acyl addition reactions to the carbonyl group that we talked about last semester. And these are actually, I think, in the 5th and 6th videos of the playlist on chapter 17. I'm going to be focused on the quiz for Tuesday on reactions that produce the carbonyl compound, not reactions that the carbonyl compound undergoes. But you should know these reactions anyway. So what are the two nucleophilic acyl addition reactions that we covered last semester?
I think there was one that turned it like into an alcohol.
Yep, so aldehydes, primary alcohols, ketones, secondary alcohols. So just as an example, benzaldehyde, could be converted to benzyl alcohol. And that name benzyl alcohol refers to the fact that this group here is referred to as a benzyl group. It's often abbreviated BN for benzyl. And so if you see BN, that's a CH or C6H5CH2. So what were the reagents for converting aldehydes to primary alcohols and ketones to secondary alcohols? We had two different reagents that accomplished that task. We refer to that as hydride reduction. We can do catalytic reduction.
Is one of them H2SO4?
Nope. That's not a hydride. Right? That's a source of H plus. We need sources of H minus.
With a dissolving metal?
The dissolving metal reduction will not convert aldehydes to alcohols or ketones to alcohols. The dissolving metal reduction, that reduces carbon-carbon triple bonds. It reduces aromatic rings.
Was it just the H2, source of H2 again?
So yes, so catalytic reduction will work. Just H2 gas under pressure with some catalysts, like the Adams catalyst, platinum oxide. Or palladium deposited on carbon, or rainy nickel. And that catalytic reduction will actually reduce carbon-carbon pi bonds as well as carbon-oxygen pi bonds. It's not usually the best way of reducing a carbon-oxygen double bond. The best way of reducing a carbon-oxygen double bond is usually hydride reduction instead of catalytic reduction. And the reagents for that are lithium aluminum hydride or sodium borohydride. So they are tetrahedral complexes. They're tetrahedral ions based on aluminum and boron, which are group 3A. Right? So we have something that when it's got a kilowatt-10 is unhappy because of the formal negative charge. And these are good sources of H minus, but a source of H minus that's not so basic that it acts as a Bronsted-Lowry base. It'll act as a Lewis base instead. If we just use an alkali metal hydride like lithium hydride, it's too basic, and all it does is deprotonate things. But by attaching it to something less electronegative, like aluminum, or sorry, more electronegative like aluminum or boron, so that we have a smaller electronegativity difference, we can get it to react as H minus. If we use lithium aluminum hydride, it has to be run in an inert solvent like ether. And then you do an aqueous acid workup. So the hydrogen that's attached to the carbon actually comes from the lithium aluminum hydride, but the hydrogen that's attached to the oxygen came from the aqueous acid. So at sodium borohydride, the solvent for sodium borohydride is ethanol, in which case the hydrogen that ends up attached to the oxygen in the alcohol comes from the solvent. So anytime you have a lithium aluminum hydride reagent, it's two steps: lithium aluminum hydride and ether, followed by aqueous acid workup. Whereas in sodium borohydride, it's enough less reactive that you can have your proton source in the reaction with you. So just sodium borohydride and ethanol. Those are functionally equivalent. Aldehydes to primary alcohols, ketones to secondary alcohols, either of those transformations with either of those two reagents. So that's one. So all we want to do now is do the other one. What is the other nucleophilic acyl addition reaction to carbonyl compounds that we learned? And then we'll be done for the day. So number one was hydride reduction. And this one will convert formaldehyde to a primary alcohol. Other aldehydes to secondary alcohols, and ketones to tertiary alcohols. You can't make tertiary alcohols by hydride reduction, because hydride reduction is always going to attach a hydrogen to the electrophilic carbon of the carbonyl group. But you can make tertiary alcohols using this other method. And then formaldehyde, because formaldehyde has two hydrogens attached, you can make a primary alcohol that still has these two hydrogens. So what reaction is it that enables us to make primary, secondary, or tertiary alcohols from formaldehyde, other aldehydes, and ketones respectively? Very nucleophilic acyl. And it's a very important reaction because outside of those palladium catalyzed cross-coupling reactions we covered right at the end of the semester for making new carbon-carbon bonds, this was the only way to form new carbon-carbon bonds that we talked about in the first semester.
Is it the organometallic reactions with the Grignard reagent?
It is. So this is organometallics. Number 2 is organometallic reactions, and you mentioned the Grignard reagents. What is a Grignard reagent? What makes something
Magnesium.
It's got a magnesium, so it's an acyl magnesium. Either the bromide or the iodide, so it's magnesium in between a halogen and the alkyl group. It acts like C minus. But because it's attached to the magnesium by a covalent bond, partially covalent bond is about 35% ionic, about 65% covalent. Because that bond is relatively covalent, it's much less basic than just a carbon anion would be, which means it won't act as a Bronsted-Lowry base, it'll act as a Lewis base instead. So we could use that same transformation to convert acetophenone by treating this with ethyl magnesium bromide. Again, that's got to be run in an inert solvent. And then the second step is aqueous acid workup. We could add an ethyl group. There you go, write that out. And so we made that new carbon-carbon bond right here. So that's one, Grignard reagents. That's actually what you're going to be doing in lab the first week. You're going to be taking bromobenzene and adding magnesium. Well, you're going to be watching me take bromobenzene and add magnesium in ether to make phenyl magnesium bromide, which immediately converts a partially positive carbon into a partially negative carbon, and then we'll add that to a carbonyl compound. So Grignard reagents are one of the type of organometallic reagents. What's the other type of organometallic reagents that we talked about?
Lithium.
Yep, lithium, alkyl lithium. So if I treated that with lithium, just solid lithium, zero oxidation state, I can make phenolithium, and I need two equivalents of lithium because one of those is going to become the lithium bromide. The alkyl lithium reagents and the alkyl magnesium bromide or Grignard reagents are functionally equivalent for your purposes. They're not, right? They are different in reactivity. The alkyl lithium is a little bit stronger nucleophile because it's about 40% ionic instead of 35% ionic. But for your purposes, alkyl lithiums and alkyl magnesium bromides can be used interchangeably to react with carbonyl compounds through nucleophilic acyl addition, nucleophilic attack by the strongly Lewis base nucleophilic organometallic, followed by a proton transfer. The electrophile is the hydrogen ion. So that's it. It's 10:08. Time things about right today. Questions, comments? You know what the quiz is on Tuesday? You'll be ready for it?
It's just filling in like reagents and reactions and products, right?
Yep. I'll give you a series of reactions that'll be missing one of the three things, either the starting material or the product or the reagent, and you'll tell me what the thing is that's missing. Should be fairly straightforward. A lot of the reactions are review.
So are they on these new reactions or most of the reactions from last semester?
Everything I talked about today that created carbonyl compounds as the product. So both the last semester reactions and the new reactions, but not these, right? Because these reactions are reactions of carbonyls rather than to produce carbonyls. You should know these, but I'm not going to quiz you on these on Tuesday. On Tuesday, we'll do some new nucleophilic acyl addition reactions to add other things rather than adding a carbon minus or a hydrogen minus, which are really strongly Lewis basic. We're going to add alcohols across and amines across and thiols and things across the carbonyl compound. And those mechanisms involve more steps. I'll send out an email telling you which of the videos in the playlist are the ones that are going to pertain to Tuesday's lecture, so you'll know if you want to watch them ahead of time. Anything else?